Good evening all. My name is Tausif Anwar and I am a research scholar in the Department of Metallurgical and Materials Engineering, IIT Madras. And actually this is a live session or you can say a doubt session or problem solving sessions where we'll be solving some sample problem similar to what you will be getting in the assignments and exams. So that you can understand the things in much better way and maximize your understanding as well as score in the exam. So this is welding of advanced high strength steels for automotive application, and here we'll be discussing about the content in the week 1, which is basically introduction to physical metallurgy of advanced high strength steels. So talking about the timeline, which shortly will go one by one. So this is basically a 4-week course, and it has already started on 22nd of August and it will end on 16th of September, and the exam date is on 30th October. It will be in proctored online mode, and enrollment is already ended. So this course instructor is Professor Murugan Amritalingam from the same department, Metallurgical and Materials Engineering, IIT Madras, and I'll be the teaching assistant for this course. So before proceeding in this course, I think how many of you are there in this meeting? Let me check. Around 5 or 5 to 6 people are there. So can you briefly tell your name and exactly what you are doing right now, and then why you took this course? So I will start with the Mohan Kumar, if you are comfortable. Yeah, Mohan. Mohan, am I audible to you? I think some issue with his mic. We'll go to other candidate like Naveen Kumar. Can you introduce yourself?
Hello, am I audible?
Yeah, you are audible. You are clearly audible.
Yeah, my name is Naveen.
Yes.
Actually, my background is of mechanical engineering, and I do have experience of 14 years in this field.
In the welding field.
Supplier quality assurance. So from that point of view, I have opted this course.
Very
and
nice.
Unfortunately, I have not received any study material of this, but I have submitted my assignment.
Okay.
Study. Help me out on that.
Yeah, sure. We can sort it out. No issue with
And,
that.
I never got an opportunity to deal with IITL like you.
No, it's fine. Like we'll try to learn. Like since you got so much experience, so I have also opportunity to learn from you. So it's not like a one way. We'll interact and we'll try to maximize our knowledge as much as we can. So it's like both way. So you can also stop me and tell me, okay, this is the right way, or this is what exactly right now going on in the field. So it's equally from both the sides. So we'll learn from each other. So
actually, the company I am working with is JVM Auto Limited.
Okay.
It's a giant in automotive ancillaries.
Okay.
Sheet metal specifically outside.
Nice.
So I do have interest in metallurgy and all.
Yeah.
And I have done AMI and Institute of Engineers India and Institute of Institute of Mechanical Engineers as well. So
Nice.
I do have both certifications.
Yeah. Nice. Well.
But my core interest is with metallurgy.
Nice.
I never got an opportunity to get in touch with this course.
Fine.
So that's why I opted this.
Nice. Thank you.
Just
Thank you.
help me on one point. Sorry to interrupt you. I need that study material of this.
We'll provide you. Don't worry.
Okay. Thanks a lot, sir. Thank you.
Thank you so much.
Thank you, sir.
Yeah. RX Arvind, can you introduce yourself?
Yes, sir.
Yeah.
Good evening to all. Myself, Arvind, from
Good.
Coimbatore Institute of Technology, Coimbatore. Currently, I am pursuing my bachelor's degree in mechanical engineering. I am quite interested in metallurgy, and also I am doing my final year project in welding, so I took this course.
Nice. Thank you so much. Tiruchithambaram Chitambalam ji. Sorry if I spell wrongly your name.
Yeah. Okay, doesn't matter. It's
Yeah.
a very typical
Yeah.
Tamil name.
Yeah.
Very old name.
Yeah.
It's Chidambaram, Lord who dances in the sky. Some very philosophical.
Okay.
I'm a metallurgist by profession,
Yeah.
but I happen to work in the Department of Mechanical Engineering as a professor. So I know what happened. I have been compelled to register for such courses.
Okay.
It's not necessary for me. You know, I'm a senior professor in the university, but some conditions I have to register for 2 courses and get one certificate for 1 course. That is why I joined this course.
Nice.
But it is quite advanced. I saw the assignment. These are all.
Yeah.
Some of the questions I never came across earlier.
We'll try to learn, sir. Don't worry. Yeah.
Very specific.
Yeah.
Very interesting.
Yeah.
And I registered for this course because I'm already familiar with the subject. And also it is only for 4 weeks. I
Yes.
don't have time. I have a lot of other work to do.
Yeah. Exactly.
So I thought I will choose this course. This is only for 4 weeks, and also I'm also already familiar with the topic.
Yeah. Correct.
That's it. Okay, thank you.
Thank you so much. Naveen Kumar, you can switch off your video. I will ask if required. Yeah. Sanjeet, can you introduce yourself?
Good evening, sir.
Good
Sir, I'm Sanjeet here. Right now, I'm pursuing my BTech from IIT Bombay, third year.
Mm-hmm.
So, I have chosen this course. I'm doing my BTech from metallurgy only.
Mhm.
So, this course I have chosen as a part of my grading.
Okay, credit transfer. Fine.
Yes.
Okay, nice, thank you. Mohan? We cannot hear you, Mohan. I think some issue is there with your mic. Okay, leave it. We'll get back to you after some time, maybe at the end of class. So, okay, thank you so much for introducing. Yeah, hello.
Can you hear me?
Yeah, I can hear you.
Basically, I'm a metallurgist having a 6.6 years experience
Yeah.
in forging. So I'm quite interested in welding. So I took this course.
Mm-hmm.
This different aspects of welding, and I took the course
Nice.
to
Thank
get
you.
the knowledge. So that's it.
Okay, thank you so much. Okay, guys, we are already 10 minutes into this session, so I would like to start with the content which I brought here. So the format of such sessions, what I planned is it will go like first of all I will be giving summary of the week, whatever we learned in that particular week. For example, right now we are in the first week of this course, so we'll first discuss the summary of what we were taught in this week 1, and then after we'll go to solve some sample problem which will be similar to there in the assignment problem, and then you go and solve the assignment problem and maximize your score. So yeah, so the topic for this week 1 is Introduction to Physical Metallurgy for Advanced High Strength Steel. So to start with, first of all, the course instructor, that professor, told about the basic physical metallurgy of normal steel, that is iron carbon alloy. So for that he showed this iron carbon phase diagram. So I hope both mechanical background and metallurgical background people are familiar with this type of diagram. So this is basically iron carbon phase diagram, where at the x-axis we have a carbon percentage, and in the y-axis we have a temperature axis. So for our importance, that is steel. So steel is up to the carbon percentage of 2.14, and beyond that it will be cast iron, right? So at different temperature and at different carbon percentage, the phases will be changing, and accordingly the properties will be affected, right? So when we talk about the steel, we'll talk about this up to here only, up to 2.14 of carbon percentage, because the maximum solubility of carbon in the in any phase, if you talk like austenite, ferrite, or delta ferrite, these are the three allotropes of iron. So the maximum solubility, that the maximum carbon that you can add into that is till 2.14% only. So we'll for our area of interest, we'll be considering these area in more details. So if you talk about the reactions or phase transformations involved when you heat them or you cool them, so there are mainly three types of transformations involved in iron carbon system. So the first one is here, reaction 1, second one is here, and the third one which is involved is here. So the first one is nothing but eutectoid reaction. We call it as a eutectoid reaction. Second one is our, can anyone tell what is the second one, if you able to recall?
Eutectic reaction.
Eutectic reaction, correct, eutectic reaction. And the third one is
Peritectic.
correct. So this is peritectic reaction. So depending on the cooling or heating, if we are cooling, then in the first reaction, what will happen? Austenite will transform to the equilibrium mixture, which is nothing but your austenite will transform to ferrite plus cementite, so Fe3C, and this mixture we call it as a pearlite, right? In the second case, what will happen? That liquid here, if you cool, it will transform to what?
So two solids.
So here like if you are at the higher temperature, then this liquid will transform to austenite plus cementite, depending on the what side of this eutectoid reaction you are. But in general, the eutectic reactions means one liquid will be transforming to solid 1 plus solid 2. So that solid may be like ferrite, cementite, or austenite plus cementite, depending on the temperature at what you are lying. The third reaction here is peritectic. Peritectoid.
Eutectic, like in the hyper-eutectic region.
Yeah.
So is it like that the cementites in the two-phase region, this austenite particles which are nucleating within the liquid, that is that is imaginable. But sir, like is it possible to nucleate that cementite particle within the liquid?
Yeah, we will come to the term hypo eutectic, so that everyone should understand. Right now we are just at the sharp that eutectic or eutectoid and or peritectic or peritectoid reaction, right?
Okay,
so we'll first understand, then hypo will go one by one, so that everyone can understand. So right, so here at the third reaction is what? We have liquid plus delta ferrite here, right? Liquid plus delta ferrite, which is nothing but one liquid, and delta ferrite is nothing but solid 1, and this will transform to other solid, which is solid 2, and that solid 2 is here what? Austenite. So the this third reaction is liquid plus delta ferrite transforming to austenite. So these three are major reaction, these three are the only reaction which is involved in this iron carbon system. Now I hope it is clear to all of you. Is it clear? Reactions are clear?
Yes, sir.
Yeah. Now just now somebody told about the hyper and hypo. So for any reaction, let's say this reaction number 1, which is a eutectoid reaction. So that eutectoid reaction occurs at a bulk carbon concentration of 0.76 weight percentage of carbon. So if you are lying left side of this carbon concentration, if your carbon concentration is lower than the 0.76, then that steel is known as hypoeutectoid steel. Hypoeutectoid steel, right? Similarly, if it is higher than 0.76, then that is called hypereutectoid steel, right? And if you are in the eutectic composition, like if you are at a very high carbon concentration, then here also you can divide it. This side it will be hyper, and this side it will be hypo, right? So these are the major reaction, and these are the nomenclature that we give to for different composition steel. Now, as I told, our interest is up to here only, and since this course is on high strength steel for automotive applications, so if you talk about the carbon percentage in those steels, so that will be very less, 0.2%, 0.15%. So that much carbon will only be there. So if you enlarge that portion of phase diagram, which is in the hypoeutectoid region of iron carbon phase diagram, so this is how the phases will be evolving. If you cool from higher temperature, let's say you are in the austenitic region, to a room temperature, or any till 400 depend. So this is how the phases will be evolving. So we have a different lines, right? So this line from here to till here will tell you, as the temperature is increasing, the solubility of carbon in alpha phase is getting increased, which will be obvious. So once when you heat them, the more and more carbon will be soluble in alpha phase, and till here it will reach to its maximum solubility, which is nothing but, here you can see 0.022% that carbon can be accommodated in alpha phase of iron, right? Now, talking about the phase evolution. So here, let's say you are at the C point, and at the C point the structure is completely austenitic here. So now you are cooling it. So once you cross this upper critical temperature, so this we call it as a upper critical temperature, this we call it as a lower critical temperature, and this is a two phase region, and this is a single phase region. So single phase, two phase, and then the mixture will come into picture. So once you cross the upper critical temperature region, which will be varying from 727 degrees Celsius, this is a eutectoid reaction temperature. So from here, depending on the carbon concentration, the temperature range may vary till 900 degrees Celsius or 910 to be precise. So once you cross the upper critical temperature, so the two phase region here is nothing but ferrite plus austenite. So what will happen? This ferrite will start to nucleate, and that nucleation will occur at the austenitic grain boundary, as you can see here. So ferrite nucleation has started, and once you cool further and further, the ferrite will grow and occupy more area, more volume. And once you cross this lower critical temperature, so what will happen? As you are cooling from a higher temperature to lower temperature, you can see the carbon percentage for, let's say, for this temperature, the carbon content in austenite is given by this line, and carbon content in ferrite is given by this point. So as you cool down, the carbon content in austenite is getting increased. Similarly, the carbon content in ferrite is also getting increased, but the main thing is the relative fraction of austenite and ferrite is also changing, so that the bulk carbon concentration remain as it is. Whatever you are taking, let's say you are taking it as a 0.2%, so the bulk carbon concentration will be maintained, and the carbon content in austenite will increase and in ferrite will increase. So once the carbon content reaches to the eutectoid carbon concentration of austenite, so here, if let's say you are just above the eutectoid reaction point at this point, so here you have ferrite plus austenite. So the austenite carbon concentration is going to just reach the eutectoid carbon concentration. So whatever austenite which you are left with will be now if you cool further, so we'll be converting into austenite. This remaining austenite will be converting into ferrite plus cementite. So this eutectoid reaction will happen once you cross this horizontal line. So at the end, if you cool this carbon concentration composition, so what you will be left with? Ferrite plus cementite. So this ferrite is we call it as a pro-eutectoid ferrite, right? This ferrite is known as a pro-eutectoid ferrite because this ferrite formed before the eutectoid reaction, and after that this mixture, ferrite and cementite mixture, will form, and this mixture is known as pearlite, right? So pro-eutectoid ferrite plus pearlite will be the microstructure. So you can see this bigger grains are nothing but ferrite, that is pro-eutectoid ferrite, and this blue and orange lamellae, they are nothing but pearlite, which is ferrite and cementite. So this is how the phases will be evolving once you are cooling your sample. So is it clear to all of you?
Yes, sir.
Yeah, thank you. So now we'll move further. So as I told, these type of diagrams are nothing but they are equilibrium diagram, but in the true sense, this Fe3 is not a equilibrium phase. Ideally it should be iron carbon phase diagram, and carbon is the equilibrium phase, but in general you can call it the phases which are evolving here are as a result of very slow cooling. So what will happen if you alter the cooling rate? So let's say just now I explained about the slow cooling. So you are in the high temperature region, that is austenitic region, and from there you are cooling it slowly. So what will happen? Pearlite will be forming, or a pro-eutectoid phase. That eutectoid phase may be ferrite or cementite depending on the carbon concentration. Now the second case is moderate cooling. If your cooling rate is higher than the earlier one, so you may end up with a phase known as bainite. Now you are cooling it very fast. Let's say rapid quenching, you are just putting it into the water to quench it. A normal carbon steel, you are quenching it, then what will happen? It will form a martensite, and if you give a further heat treatment, tempered martensite will form. But in general, this as a result of different cooling rate, we may have pearlite, bainite and martensite. So why I am telling the cooling rate here is because whatever microstructure you generate using any heat treatment, but once you are going to weld them, so during welding the temperature will go to very high, like 1000, 2000, depending on the material or the filler or the welding process that we are using. So the welding during welding the temperature will go very high, and when you finish the welding, the temperature, that high temperature and your welding condition will be ambient. So that temperature difference will be giving you a very high cooling rate, right? If you are not using any technique to slow down the cooling rate. So whatever microstructure you created earlier, and you just after welding, it will be destroyed. Maybe if it is a normal carbon steel, it will form martensite, and martensite will be very hard. That will end up with a cracking and all. Many issues will be coming. So to understand the what is the start microstructure and what is going to be happen during the welding, and what will be the result after welding. So all these things you have to correlate before going for any part fabrication. So this is how the cooling rate will be affecting the microstructure. Now to understand the phases that will be evolving as a result of different cooling rate, we have two types of diagram. The first one is time temperature transformation diagram, which is shown here, and the next one I will be showing in the next slide. So this is time temperature transformation diagram, and here the transformation is considered isothermally. So from what temperature you are cooling, and you're cooling, and then you have to hold it at a constant temperature, and you have to observe the transformation. So it's not like you are continuously cooling and you are seeing the phase evolution. It's not like that. You have to hold it at a certain temperature and then you see when the transformation is starting and when the transformation is ending. So this diagram, TTT diagram, I have taken it for the composition of eutectoid steel. So this is a TTT diagram of eutectoid steel, and for different steel the diagram will be changed, right? Because the phases will be changing, so it may shift right, left, or some other phase may appear. So that we can do, but here it is shown for eutectoid composition. So here what we can learn from this diagram is how the phases are, like at what time which phase will appear and at what temperature it will appear, right? And if we alter the cooling rate, what will be the effect of cooling rate on our microstructure? So here you can see, let's say I am following the path A, B, C, D. So before going into the ABCD, I will first tell what is this red line is, this blue line is, and the green line is. So what is the eutectoid direction? What is happening in the eutectoid direction? Can you just tell?
The austenite is changing into ferrite and cementite.
Ferrite and cementite, right? So ferrite and cementite, that is like perlite only, right? So this red line is nothing but the perlitic start, like when your perlite is start transforming from austenite, and this green line is the end of transformation, like your complete austenite got transformed into the perlite, and in between it is a 50-50%, like 50% austenite and 50% perlite. So this is what these lines are indicated here. Now you are cooling it from a austenitic region. So above 727 in the phase diagram, if you see here, so this is 727 temperature. So if you are above this diagram, you are into the austenitic region. So if you are in the austenitic region and you are cooling it, the cooling rate may be different. So here it is like this. So when you cool it and you hold it around let's say 620 degrees Celsius, so what will happen at the C, the perlite austenite to perlite transformation will start, and at the D it will be completely perlitic structure. So this side of left side of red line, it is completely austenite, and right side of this green line, it is completely perlite. Now depending on the what region, like if you are going like this or you are going like this, that will dictate you the size of these phases. So if you are at the higher temperature, let's say 650 degrees Celsius, and then you are holding it isothermally, then that perlite will be coarse perlite. That size of perlite, if you see, that will be a coarser. And if you are at a lower temperature, if you are isothermally holding it, then in that case the perlitic structure will be very fine. So here it will be fine perlitic structure. So this is what we can get it from TTT diagram. But the drawback of this diagram is in the actual practice we do not hold it. Let's say you are doing welding, you welded it and you just stop welding, and then what will happen? It will cool continuously. But here it is isothermally hold it. So this is not much commercially applicable diagram. So to improve this, we have another diagram, which is a CCT diagram, continuous cooling transformation diagram. So here, instead of holding it isothermally at a certain temperature, we will be continuously cooling, like in actual practice, right? So then this diagram will tell what phases you will be end up with if you are dealing with the different cooling rate or temperature at which you are crossing it. So here you can see there are basically three regions. First region is like from here to here, second region is from here to here, and the third region is starting from here to here onwards. So this dotted lines are nothing but cooling rates, showing the cooling rates, different cooling rates. Let's say this is 8.3 degrees Celsius per second, this is 0.3 degrees Celsius per second, and this is like very slow cooling rate, and this is very fast cooling rate. So what will happen if you go with the very slow cooling rate, like 0.006 degrees Celsius per second? So what microstructure you will be getting? or if you are doing it very fast, 8.3 degrees Celsius or even more than that, what will be your microstructure. So this diagram will tell you final phase. So to understand this diagram, what will happen, let's say I'm talking about this cooling rate. So this is nothing but, this line is nothing but, and for more one more thing is that this diagram is drawn for a hypo-eutectoid steel, right? So this diagram is for hypo-eutectoid steel, and the earlier diagram was for eutectoid steel. So this is a hypo-eutectoid steel. So once you let's say you are cooling it from a higher temperature, that is about 727 to a lower temperature region. So once you cross the this 727, once you cross this upper critical temperature, what will happen? Like here you can see, here once you cross this upper critical temperature, then your ferrite will nucleate. This pro-eutectoid ferrite will nucleate, alpha, and then gamma will be getting decreased and alpha will be getting increased. So similar to that also here, this is what austenite to ferrite transformation line, and after that whatever remaining austenite is there, after this line if you cross, the remaining austenite will transform to pearlite and the ferrite will be remain as it is. Then the final microstructure, if you see, then in the final microstructure it will be like ferrite plus pearlite if you go with this line, right? Now this middle line is saying what? This middle line is telling the pearlitic transformation line, and the critical cooling rate to avoid this pearlitic transformation is this cooling rate. So if you are right side of this yellow line, then pearlite will form. Pearlite is going to form. You cannot avoid it. But if you are at the left side of this middle line, then you can avoid the pearlitic transformation, and you can have other types of transformation. That is, from here what will form? Ferrite will form from austenite, and the austenite, remaining austenite will go and follow this, and once you cross this line, which is a banetic nose, then the austenite will start transforming into austenite into bainite. So we have ferrite, from austenite to ferrite transformation. Now the austenite is transforming into bainite, so we got bainite also. And then there is a line here, you can see the dotted line. So this, if you cross this line, right, so you have austenite already, then this line will be after this line, that is M start, which is martensitic start line. What will happen? The austenite which you have in the matrix will try to transform into martensite. So you got ferrite, you got bainite also, you got martensite also, and then if you come down to the room temperature, then there will be a little bit of austenite maybe retained, that is retained austenite. So such a like martensite, ferrite, bainite, pearlite also you can form if you are just crossing this region, or if you are avoiding this, then pearlite will not form. So such a complex microstructure you can generate, right? Similarly, if you are like this banetic nose, if you are avoiding, then instead of forming bainite, you will directly form austenite to martensite. This reaction will happen directly, austenite to martensite. So for that you require a very high cooling rate, and then this austenite will transform to martensite. So completely martensitic structure you can get if you are avoiding this this nose. So let's say this cooling rate is like this, so you can directly end up in the martensitic region. So I hope it is clear. CCT and TTT is clear to both both the diagrams are clear to all of you?
Yes, sir.
Yeah, okay. So we can go ahead. Now we talked about the depending on the cooling rate, we talked about the three types of phases or a mixture. For example, if you are cooling it very slowly, then what we were getting is, we were getting pearlite, or intermediate, that is bainite, or a very fast, that is martensite. So how these things are formed, that sir has explained in his lecture. So this pearlitic transformation is nothing but what will happen if you cross the upper critical temperature, then or let's say you are at the exactly eutectoid carbon concentration, then ferrite will nucleate at the austenitic grain boundary and it will grow, and ferrite has a very low carbon solubility, so it will reject the carbon nearby, and due to rejection of carbon, this carbon rich iron phase, that is cementite, will be forming, which is in the blue color, and like that this ferrite and cementite, which is nothing but perlite, this perlite will be growing and it will consume the austenite and it will be fully perlite at the end of transformation. So this is how the perlite will form. Talking about the bainite, so you can see here we have a like carbon supersaturated plate, or you can say lens shape. So depending on the temperature, at what temperature you are cooling it from that high temperature region, we can have two types of bainite, upper bainite and lower bainite. So upper bainite forms at like if you are giving a slightly low cooling rate compared to the lower bainite, and the morphology of both the bainites will be different. So here you can see we have this ferrite lens, and in between these two ferrite phases we have cementite, that is carbide got trapped between these two ferrite phase. And here in the lower bainite, since the cooling rate is very fast, so your carbon is not getting that much time to get diffused outside of this ferritic boundary. So inside also some ferrite is forming, a cementite is forming, and a little bit of cementite in between these two ferrite. And talking about the martensitic transformation, so here in both this perlitic and bainitic transformation, diffusion is involved. Like carbon is diffusing from ferrite and forming cementite. Here also carbon is diffusing to form a cementite. But this martensitic transformation, it is a very rapid. Like you are quenching it and you are not allowing it to, not allowing carbon to get diffused and form that equilibrium phase. So here the diffusion, we also call it as a diffusion-less transformation. So this martensitic transformation is also called diffusion-less transformation. So here diffusion is not happening, but the transformation is happening due to shear, right? So you can see this this is a austenite matrix, that is a FCC, and this austenite is transforming into martensite. That the crystal structure of martensite is, does anybody know what is the crystal structure of martensite?
Sir, body center tetragonal.
Yeah, so that is BCT. So and this transformation happen in a diffusionless manner with the help of shear and dilation, and this is how we get a hard martensitic phase. So these three phases are very important, so that's why I explained it here. Now coming to the microstructure, how they look like. So this is how perlite will look like. So it will be like fingerprint. If you give your fingerprint, it will look like this. So this white phases are nothing but ferrite, and this black phases are nothing but Fe3C. So lamellae of ferrite cementite. This is how perlite will look like. And in this this is a TEM image, translation electron microscopy image. So here you can see we have martensite as well as bainite. So this region is of bainitic region. So here in the bainite you can see this is our ferrite and this is our cementite, Fe3C. So maybe this may be of lower bainite, where you can see in the ferrite itself the cementite needles got trapped. They didn't get time to go outside and form some carbide. So this is a cementite and this is a ferrite, and this microstructure is of martensite. So martensite, you can see sharp needle shaped martensite formed as a result of very fast cooling rate. And the white phase here is nothing but, what is white phase here? Can anyone recognize? This black phase is martensite.
Sir, it is the retained austenite.
Yeah. So this is nothing but our retained austenite. So retained austenite plus martensite. So this is how these three microstructure look like, right? So far what we learned, iron carbon phase diagram, then phases for a carbon concentration less than the eutectoid, that is hypo, and then how those phases will be forming, and then how they will look like. Now coming to the actual practice, where we'll be using other than carbon, some other allying elements will be there, like you can see the composition here. So the effect of allying element on this CCT or TTT curve that we should understand very clearly. Then only we can play with the welding processes. So here you can see this black line is ferrite start line, and this green line is pearlite start, pearlite end, ferrite end, and this blue line is bainite start. So if you take any cooling rate like this, so what is happening? You are forming pro-eutectite ferrite, and then if you are going this way, then pearlite, and then if you are crossing this Martensite temperature, then Martensite. But from this to this transition to happen, what people have added is just 30 ppm of boron. So 30 ppm of boron is added to this composition, and you can see the drastic change. Initially for this cooling rate we were getting this ferrite, then bainite, then martensite, but for the same cooling rate now we can directly form martensite. The that CCT curve got shifted towards right. So and due to that for the same cooling rate we are getting directly martensite from austenite. So this is how the alloying element can shift your CCT diagram towards right or towards left. So whenever you are using a new alloy or new steel, you should understand where my cooling rate, how is going to change my microstructure. So using CCT diagram that you can evaluate. Now then sir came to this various generation and as advancement into the steel for automotive applications. So we started with the generation 1, then generation 2, generation 3. So here you can see like the overall summary of this diagram, we call it as a banana diagram. So here what we want is a for a current norms, that is Bharat stage norms, whatever norms we are living right now, Bharat stage 6 or in future BS 6, 7, 8. So for that, to follow that norms, the CO2 emission we have to look for. So we have to minimize the CO2 emission. At the same time we have to look for the safety, like strength and then formability of steel which you are using, and CO2 norms like in terms of fuel consumption. So all these things you have to look at a certain when you are choosing a material for a automotive body parts. So our as the time is moving from generation 1 to generation 6, 7 Bharat stage generation, so our aim is to grow diagonally. So we don't want to compromise strength on the cost of elongation or elongation on the cost of strength. So we want to grow, we want tensile strength to increase, at the same time elongation should also increase, because this strength will give you like crash proof. If you have a very high strength material in your automotive body, then that crash you can avoid. Similarly, if you have a good elongation, then you can form it. Let's say you are able to form a steel with a very high strength, but you are not able to give any shape to it. So that is also not going to work. So we want both good percentage of elongation as well as good tensile strength. So our aim is to grow diagonally. So as the time passes, this development in steel went on, and right now we will talk about this advanced high strength steel grades in this course for automotive applications. So if you want more detail of IAS, IF, BH, DC, CP, TRIP and all, you can go and just watch this lecture again. You will get clarity. Now then sir has started to move into the high strength, lowest alloy steel, TRIP steel and DP steel. These steel we started discussing. So if you see the engineering stress strain curve of these three steel, for a given yield strength, that is 350 for all these three, you can see the fracture strength, like at what strength it is going to, or this ultimate tensile strength I think it is. So the maximum strength that you are going to be get will be different for a given yield strength. And one bad thing about this HSLA steel is, you can see here, this steel is undergoing a phenomena known as yield point phenomena. So what is that phenomena? Does anyone know yield point phenomena?
Sir, the solute atoms basically they segregate below the line of the dislocations, so they do not allow the dislocations to move forward. So basically, we need to provide an extra stress in order to
Detach those solute atoms.
The capture of the solute atoms.
So that solute atom can be of any type, like interstitial or solid,
No, sir.
substitutional.
Like it depends on the alloy. Like in case of iron, it is generally an interstitial element. But when we talk about the aluminium alloys, sometimes the substitutional elements also cause this.
So in iron, what element it is? Like if right now we are talking about steel. So which element is going to pin the dislocation?
Sir, the carbon, nitrogen, like that.
Carbon mostly, right? So this carbon, what will happen? Let's say you have a dislocation line, right? So this is the edge dislocation line. So what will happen? This carbon atom will go and decorate below the dislocation, and it will pin the dislocation. So if you want to move this dislocation further, so you have to break the bonding between this carbon and dislocation line. So in order to do so, you have to apply some extra stress. So this is why this maximize, that peak is coming, and then further it will be detaching, and then you can further move. So this phenomena is not desirable if you consider the metal forming part, because once you are deforming your material, due to this yield point phenomena, that bands will be appearing. That band is known as Luder band. So Luder band, it will not look good to your eye, like it will look like a defect or some scratch marks on the sample. So considering that, it is not at all a good phenomena in case of if you are deforming your material. So HSLA steel is having that disadvantage. Also that strength, if you are seeing here, that is 450 only compared to 600. At the same time, DP and TRIP, they do not show any yield point anomaly or yield point phenomena. So they are much better compared to HSLA. Now coming to the heat treatment, or how DP or TRIP steel are formed, or let's say like what are the microstructural constituents in the DP and TRIP steel, that sir has taught. So can you tell what microstructure it is, like which steel microstructure it is?
Sir, it is a hypoeutectoid steel.
What? Sorry?
Sir, it is a hypoeutectoid steel.
That's correct. Smart answer. But yeah, so it is a nothing but dual phase steel, DP steel. So DP is nothing but dual phase steel. So what is the microstructure, microstructural constituents in the DP steel? That is nothing but ferrite plus martensite. So martensite we denote it as a alpha prime. So alpha and alpha prime. So this dark phases are nothing but our ferrite, and here these are nothing but martensites. Apart from this ferrite and martensite, what we have at the ferrite and martensitic interface, which is shown here as a line, white lines you can see. So we have a large amount of mobile dislocations, right? Mobile dislocations. So from where this mobile dislocation is coming? So the source of mobile dislocation is like when you are cooling this austenite to martensite, so there will be a volume expansion, right? Volume expansion. So volume will be changing, and to accommodate that volume, large number of mobile dislocation will have to come at the ferrite and martensite interface, and that mobile dislocation is nothing but you can see here in the line. So now the best part of this DP steel is we have a soft phase ferrite, we have a hard phase martensite, and for the deformation we have a mobile dislocation. So this is what actually we want. We want formability, that is ductility, we want strength, and we want mobile dislocation will basically help you to make parts. So to get this to get such a microstructure, we have to like play with the heat treatments. Like we have to give some special heat treatment, as well as we have to give we have to add some alloying element if needed. So this is how this dual phase microstructure will look like, and we get. Coming to the other, which is nothing but a trip steel. So what is the full form of trip?
Transformation induced plasticity.
Okay. Yeah. So here you can see the microstructure of trip steel. So as you can see clearly, here is the microstructure consists ferrite and a bainite and a retained austenite. So this bainite will give you strength, ferrite will give you ductility, and this retained austenite. So why we call it as a transformation induced plasticity. So during the load application, let's say this is your microstructure, and your like if you are hitting your car by a hammer, or your car is hitting some wall, so then the load will be applied to this structure. So during the load application, this retained austenite here will be transforming into martensite. So during the transformation, it will get hardened. So this is a best part of this steel. So it can give you a very good crash resistance. So from austenite to martensite transformation, it will happen by stress application. So you can also call it as a stress induced transformation. Here the transformation is not happening due to quenching, as usually like happen in austenite to martensite. The transformation is happening by the application of load, that is a stress induced transformation, and during that transformation your material is getting harder and harder. So that will give you a crash resistance into your microstructure. So to get such microstructure, what we have to give is we have to give some critical heat treatments. So sir has already explained these heat treatments in detail. So basically we heat it to two-phase region, that is intercritical region, and from there we quench it or cool it rapidly to bainitic start temperature, like, or below bainitic start temperature, and from that we will cool it to room temperature. So we get ferrite and bainite and this retained austenite. And this bainite is not a conventional bainite. This is a basically carbide free bainite. So we studied about the upper this high temperature bainite or lower temperature bainite. So this is not that high temperature or low temperature. This is a carbide free bainite. So in this bainite, it will be only a ferritic matrix. No carbide will be formed, and this ferrite matrix will be enriched in carbon. So these are nothing but carbon supersaturated ferritic matrix. So we call it as a bainite. So which is nothing but supersaturated ferrite, that is bainite. That's why I showed it with the alpha. Alpha is symbol of ferrite and a kind of bainite. So yeah, so that's all from the summary of this week. If you have any query, you can ask, and if not, we will move to some sample problem. We'll try to solve them, and then we will wind up this session. So if you have any problems so far, you can ask, we can discuss. Mohan, Naveen Kumar, Arvind, Sanjeet. So if it is clear, then we can go to the question, and by question I can understand whether you have understood the thing correctly or not. So shall we go to the question now?
Yes, sir.
Yes, sir.
Okay, fine, thank you. So the first question you can see here, question is, which of the following transformation is known as incomplete reaction phenomena? So I request you, like, you can type your answer in the chat box and then I can see. And if I ask somebody to give justification, then he can unmute and then give justification. So for question number 1, you can type your answer in the chat box and I can see them. So this is a question. The important point here is incomplete reaction phenomena. I think all of you are done with the answers. Only 3 people have replied. What about the Mohan already commented. Tiruchirambalam ji, and then Sanjeet has already commented. Yeah. So I will tell you the answer. So if you are cooling your austenite phase, so this ferrite or cementite or perlite, like these are the result of equilibrium cooling. If you are cooling it very slowly, so there is nothing retained in it. So you might have seen in this curve here. When you are crossing this line, or if you are towards right side of this cooling rate, your microstructure will be ferrite plus perlite, and there is nothing retained, like retained austenite, or like whenever you are forming bainite or martensite, there will be some retained austenite. There is nothing like complete martensite transformation. Like to get that, you have to cool it to a very low temperature. Like in general, you have to go subcritical temperature in minus temperatures. So whenever you are forming martensite or you are forming bainite, so you will be left up with some retained austenite. So in that case, so that reaction is incomplete because your high temperature phase is still there, which is austenite. So this mixture, martensite plus retained austenite, is not that that nature wants or equilibrium wants to give you. But if you are forming this ferrite and perlite, there is nothing like retained austenite. So your austenite is completely transforming into perlite or ferrite depending on the carbon concentration. So here in the options, the correct answer is austenite to bainite. If it is, if in the option, let's say the option is austenite to martensite, then option E will also be there and option C will also be there. So austenite to bainite is a kind of incomplete reaction phenomena that needs to further react to form a equilibrium phase. So the right answer is option C. Now question number 2, what is the full form of TWIP? TWIP I told you. So we have other type of steel, that is TWIP. So you can tell your answer in the comment box. So the right answer is option B, that is twinning induced plasticity steel. I think someone has commented A, that is transformation with induced plasticity. That is not a correct. That is related to TRIP, TRIP, transformation induced plasticity. Like if you want to transformation, then you have to do plastic deformation. So that plastic deformation will cause you austenite to martensite transformation. But here in the TWIP, TWIP, the full form is twinning induced plasticity steel. So this is the correct answer. So do you know the mode of like if you want to deform any material, or like if you want to do this plastic deformation, there can be a two way. The first way is twinning, other way is dislocation glide. We call it as dislocation movement. So in this steel we induce the plasticity with the help of twinning. So this steel is nothing but austenite. Like the microstructure of this steel consists austenite, mainly like austenite only, and the twinning mode of plasticity will be the main highlight of this material. Yeah, coming to the third problem. Typical microstructure of dual phase steel used for automotive application contains. Go through the options and comment your answer. I think so I'm asking about the DP steel. So all of you have mostly like commented option C, which is correct, ferrite and martensite. So I showed you also earlier this microstructure. So the DP steel microstructure dual phase, that is ferrite and martensite with mobile dislocation at the interface. So the microstructure constituents are ferrite and martensite only. So this is what a dual phase steel consists. Is it clear? Hello? Hello? Am I audible?
Yes, sir.
Yeah.
Okay.
Yeah. So if it is clear, you can solve this question number 4. A HSLA steels which has an identical yield strength to a dual phase steel, then I explained this using this engineering stress strain diagram. So from that only this question is. So if you have a identical yield strength, then what will be the difference in total elongation? It will be same, higher, lower, or some other phenomena will come into picture. Yeah guys, comment your answer if you know. Don't worry if it is wrong also, then it's fine. Don't worry. We are here to learn something. You can type your answer based on your understanding, and if it is wrong, we will discuss. Yeah, Sanjeet and Arvind got it right. DP steel would always show higher total elongation. So for this problem, I mentioned this diagram. This diagram you can see here. For the same yield strength 350, 350, 350. So HSLA, TRIP and DP, all these three have almost same yield strength. But if you talk about the total elongation, so in the problem it is asked about the DP steel. So you can see DP steel total elongation is much higher compared to this HSLA steel, right? So that's what it is asked in the question. So DP steel would always show higher total elongation compared to HSLA. This option is like reverse one. Both steel should exhibit yield point phenomena. No, it's not true. Only HSLA will exhibit yield point phenomena. DP will not exhibit yield point phenomena. DP steel would start to neck at a lower strain level as compared to HSLA. No, they are almost like DP steel will be having a slightly higher compared to HSLA. So only option correct here is option A. Now we'll go to next question. Question number 5. compared to silicon and aluminum in the steel. So what is the effect on solid solution strengthening and the tendency to form oxide, which will be having higher solid solution strengthening effect and oxide forming capability. Okay, Arvind has commented. Only 2 comment I got. Okay, Mohan also. D. Okay, D. So, like this question is in the context with trip steel. So, if you classify trip steel, they are basically of 2 types. The first one is silicon based trip steel, and the second one is aluminum based trip steel. Right. So in one case silicon will be the main alloying element, and in the second case aluminum. So in the silicon based trip steel, we add silicon only up to 1.5 weight percent, and in aluminum it goes up to 1.1 weight percent, and apart from that you will have manganese and the carbon, other alloying element in both the steels. So the main highlight of these 2 steel is when you add silicon and aluminum, they will their solubility in like cementite is very poor. They cannot be together with the cementite. So when they are present there, then you will not going to form a cementite, right? But both these will be having like different magnitude to affect this. So this aluminum, if you compare, so aluminum will have a like very high tendency to form oxide compared to silicon. This aluminum will immediately form aluminum oxide Al2O3 when you are adding this into the microstructure. And talking about the solid solution strengthening, so aluminum is a poor solid solution strengthener compared to silicon. So if solid solution strengthening if you are talking, then aluminum is poor compared to silicon. But if you talk about the oxidation, oxide forming capability, then aluminum is better to form oxide than silicon. So the right option is option A as well as option D, poor solid solution strengthener and strong oxide former. So these 2 are the correct answer for this problem. So I think most of you got correct partially. Arvind got it exactly what he told A and C. Okay, he also got partially correct. Now come to the question 6. Solve it. Austenite is retained in trip steel upon heat treatment by you can unmute and say your answer, because I think you are less interested in typing, so you can unmute and tell your answer, or you can tell
These questions, these questions are from some research articles, it seems. We have not studied this. It's not normally found in textbooks. I used to refer to a textbook by Professor Raghavan. He was a professor at IIT Delhi. I don't know whether he's still alive. He was a great professor of physical metallurgy. I used to refer his books.
yes, sir.
Such information was not available in those books even.
Sir,
from research articles. Okay.
Sir, if you want to solve such problems, I will suggest you only one thing. Whatever weekly content, video lecture that we are uploading weekly, just follow those lecture by heart. Just listen all the lecture very sincerely.
And take down notes. I usually take down notes.
Yeah, and then take down notes, and then if you do so, you will solve all the problem. All these problems are from there only. They are not new. Yeah. So by this I can also check whether you are watching the videos or not. So if you carefully watch the video, you can simply, like, you can at least 80%, 70% got your answer correct. So yeah, that's my suggestion. For exam purpose and assignment also, you just follow the lectures, and if you're getting in doubt, we are here to discuss. So don't worry about it. So yeah, so you can solve question number 6. I think 3 people commented their answer. B, somebody is saying B and D. So austenite is retained in tripped steel upon heat treatment by. So the right answer is B and D. So what is happening when you are forming the strip steel? So the heat treatment will be in the two-phase region. So let's say this is, sorry, I will redraw it. This is a hypoeutectile section of your steel. So what we do is we heat our steel to a intercritical region, that is between this and this temperature, and we hold it there. So by doing so, let's say our carbon concentration is 0.2 weight% carbon. So if you heat your sample to this temperature, so this line will dictate you carbon concentration in gamma, and this line will dictate you carbon concentration in alpha. So your bulk carbon concentration is 0.28% only, but when you heat them, your carbon concentration in gamma will be this much. This will tell you gamma carbon concentration, and your carbon concentration in alpha will be this much. So you can see the carbon in alpha is very, very low, and the carbon in gamma is very, very high, but the overall carbon concentration is 0.2 only. So basically in the two-phase region, you have bulk, initially you have bulk carbon concentration 0.2 only, but in two-phase region, if you are holding it, your gamma is getting enriched in carbon. So here it is 0.2 and it is more than 0.2. So gamma carbon concentration is greater than 0.2 weight%. So your carbon enrichment in austenite is taking place in the stage 1, where you are heating your sample in the two-phase region. So carbon enrichment in austenite. The second is D, incomplete austenite to bainite transformation. So tripped steel itself, what is transformation induced plasticity? So you want to retain the austenite in your microstructure, right? So retain austenite you want, so that this retained austenite get transformed to martensite. Doesn't matter if some bainitic transformation is taking place, you don't want this austenite to get transformed to bainite. I will show you that heat treatment cycle, then you will understand it better. So here the first stage was heating to an intercritical region, so that alpha and gamma was forming, and then you are cooling it to form bainite. But you don't want to form complete bainite, this ferrite and bainite, and you want some retained austenite to remain as it is, so that it can provide you crash resistance to martensite. So incomplete transformation of this alpha bainite to austenite to alpha bainite. So two options are correct here, option B and option D, and I think 2 people got it right. Well done. We'll go to next question. When undeformed austenite transformed to lower bainite, then what will happen? Read the, this retardation of cementite precipitation. This option is related to the alloying element, which is like more related to addition of aluminum and silicon. If in the question, if it is asked effect of aluminum addition and silicon, then option C will be the we can choose, because the addition of aluminum and silicon is causing the retardation of cementite in the matrix. But here it is asking about the austenite is retained. So to retain the austenite, there is no role of cementite here. The only role is carbon enrichment and this incomplete transformation. So Arvind, you got it? if in the question if I ask aluminum and silicon roll, then you can say retardation of cementite precipitation. But here it is related to austenite transformation, then you can say it like that. Question number 7 you can solve. When undeformed austenite transform to lower bainite, austenite to lower bainite, bainite that to lower one, what will happen? So be careful when you are reading intra and intralath and interlath. So this is the only trick here. So I'll show you that diagram again, then you will recall it. This. So I told you about the bainite, two types of bainite. The first one is upper bainite, and which forms at a higher temperature, and the second one is lower bainite. So in the upper bainite, which forms at a high temperature, and lower bainite, it forms at a relatively low temperature, we have enough time to we have enough time, and we have given enough time to carbon to go and form a interlath, these two are laths, interlath cementite, right? We gave enough time to form interlath cementite, but here since we are cooling it very fast compared to this one, so the carbon in the matrix will not get enough time to form a interlath cementite, very less. So instead of forming interlath cementite, we will be forming intralath cementite. So inside the ferrite matrix itself, the cementite will be forming. So now you can read the question. So when undeformed austenite transform to lower bainite, intralath precipitation of cementite occur due to sluggish diffusion of carbon. Why sluggish? Because the cooling rate is very fast. You are not allowing that them to get diffused. So the right answer is option A. Good. We are cooling it, Sanjit. So we are cooling it from high temperature phase. When undeformed austenite, let's say we are cooling it from high temperature phase to form a bainite. So this recovery recrystallization, that will come into picture when you are at the room temperature, or like you are having some hard phases or some high number of dislocations, and you want to eliminate them. Then you do heat treatment to have this recovery recrystallization. These two are just to confuse you. The only thing here is interlath precipitation of cementite due to sluggish diffusion of carbon. Yeah. Question, yeah. Question number 8 you can solve quickly. Hot forming steel are deformed when the temperature is good. So in the hot forming steel, what the name itself is telling, the right answer is C only. So we heat it to a region where we have austenite, and we do the forming in the austenitic region only, and then we will cool it, right? So after cooling, if you cool it very fast, the microstructure will be having martensite. So you can form it as you want at high temperature, and you can also get the martensite, that is a very hard phase. So formability as well as strength, both you can get if you are using this hot forming steel. So I think everyone got correct. Option C, fully austenitic region. this question 9 you can solve. The microstructure of the components made of hot forming steel, the same steel which I told, contains. So I already told you the answer, just you have to type. Yeah, so it's very clear. After deforming at austenitic temperature, we cool it to form martensite. So you start with the ferritic or palladic microstructure, you heat it to a complete austenization, you deform it there or do hot forming, and then cool it to form a martensite. So martensitic microstructure will have. Last question. Yield point phenomena is generally not seen in. Okay, so everyone is saying D, and it is the right answer. So can
Sir, I think sir, both options will be there, B as well as D also.
extra deep drawn grade steel? I don't think so.
Sir, because like in case of extra deep drawing steels,
Yeah, ductility will be improved. Yeah,
sir, like we don't want stretcher marks to be seen on the surface.
Yeah,
This yield point phenomena is also the cause
yeah,
of the
correct.
stretcher.
I thought it is ED, but here it is extra deep drawn. Where also we are locking the, like we are adding some carbide formers, maybe some niobium, titanium, vanadium. So similar to this interstitial free steel, they will be combining with carbon or nitrogen, that interstitial atom, to form carbonitrides, maybe carbide, sometimes nitrides, and they will impart you the strength. And at the same time, if you trap the carbon using these alloying elements, so what will happen? You can eliminate the yield point phenomena. So without having this anomaly in the stress strain diagram, you can simply, like, smoothly you can move and then deform it. So yeah, extra deep drawn and interstitial free steel, both will not see the yield point phenomenon. Correct. This already covered, right? Yeah. So these are some of the references which I used for these slides in this lectures. And thank you so much. Now, if you have any doubt in the question or what I summarize, then you are free to ask. And I suggest you to go and do your assignment problem after listening to this live session. And if again, if you feel any doubt in those problems, we can discuss it maybe next. Yeah, notes. So this slide as well as the recording, the same will be appearing in the Swayam portal. Maybe within 1 or 2 days it will be uploaded, so don't worry about that. Slides as well as live session recording, you will get it within 1 or 2 days. So after every live session, these slides and recordings will be uploaded. So I hope it answers your question. You will get both, don't worry. Yeah. Yeah, welcome. So if you want to give any feedback, you are most welcome. Okay, highly advanced. So you want me to explain it more slowly or in more detail? In what way? You can unmute and say, sir, we are here to listen you.
No, it's okay. It's okay. No, for me, no. What is my opinion is that, IIT standards are very high. They want to differentiate different set of students. In IIT you find IIT students are very brilliant. So they want to categorize students in order to categorize standardized students, they formulate twisted questions. And it is of no practical use. No? These are all highly advanced.
No, sir. Like my only one.
For example, aluminium, as whether it forms, tends to form cement, tends to suppress cementite or not. It's okay. So, academic interest. We are here to, we are all academic students, we are interested in completing this course. But my role as a professor is different. Okay, that is a different matter altogether. I am forced to do this. Okay, that's okay. Thank you.
My only suggestion.
Excellent support. Thank you.
My only suggestion to you will be, sir, just watch the lectures.
Okay.
If you watch the lectures, I don't think you will get any difficulty to solve these problems. And if you watch the lecture properly and if you solve the problem, then in the actual application also all these things will be visible to you, because you will be having the background and problem solving, then it will be visible. So that's the only suggestion I have.
Because you don't have extra time to read lot of other materials.
Just follow the lecture, sir. It will be enough.
Lecture and this support will be very good. So that you will understand what type of questions are expected.
So these sample problems, if, now you have solved all the 10 problems. I will suggest you just to go now and solve the problem in the assignment. I hope you will solve all the problem. I am confident that.
Okay,
Thank you so much for your feedback. Bye. Any other feedback? Or if it is okay, then we can continue the sessions, 3 more sessions like that. And if you want any change, you want problem first, then solve, then the explanation, that also we can do. Or any other method also we can have. But you should learn, and parallelly me too. Like if you are having some other practical experience, you can share it with all the people in the meeting. So thank you so much for joining this live session. Then we'll meet again on next Friday, 7 to 8. Right? And
thank you, sir.
In between you go and solve the problem. Thank you so much. Thank you.
Thanks a lot.
Thank you, sir.
Okay. Bye.
thank you.
Okay.
Bye.
Thank you so much.